So we're going to finish off section 4.2. If you're watching this, hopefully you have already completed the left rectangular area method, right rectangular area method, midpoint rectangular area method worksheet, and you have an idea about how to find the approximate area bounded by a curve. Now we're going to try to find the exact area bounded by a curve. So that's going to pull in the formulas that we saw on day one of this section, one of them being this summation from I equals 1 to n of I being equal to n times n plus 1 divided by 2. If you recall, that had to do with the fact that we could add 1 plus 2 plus 3 plus 4 plus 5 all the way up to n minus 1 and up to n. And when you added the first plus the last term and the second plus the penultimate term, etc., we could derive that formula. All right, so just as a refresher, we've got that formula. So we're going to start using that in other ways. So for example, if we look at that summation, it's almost the same. We still have an I in there, but we also have a 5 in the numerator and an n squared in the denominator. So the question is, how do the 5 and the n squared affect things? Well, if we think about what's going on here, I'll expand it out up here. We've got 5 times 1 over n squared. We'll go ahead and put the 1. And I also have 5 times 2 over n squared. And I just keep on going. I'm going to have 5 times n minus 1 over n squared. And I'm going to end up with 5 times n over n squared. So you're going to notice that each one of these terms, we've got n of them, and each one of these n terms has a 5 in the numerator and an n squared in the denominator. These aren't changing as the I value, the counter variable, progresses. It starts at 1, and then it goes to 2, and it goes to 3. So I keeps on changing, but the 5 and the n squared don't change. So since they are constant with respect to I, they're not changing with I, then I can factor out the 5 and I can factor out the n squared. This is a common factor in each of my terms. All n of them have that 5 over n squared as a factor. The only thing that is changing is the I, so I'll leave the I in there. But we already know that that equals n times n plus 1 over 2. That's what that sum equals. So we have 5 over n squared times n plus 1 over 2. And if you want to, you can rewrite that as 5n times n plus 1 over 2n squared. It's the same thing, just a slightly more compact way of writing it. So what? Well, now what we're going to do is we're going to take that limit. We're going to take the exact same summation, and we're going to take the limit as n goes to infinity. Well, so we already evaluated the sum, so we're going to take the limit of the sum, but we just found that that's 5n times n plus 1 over 2n squared. So as n gets very, very big, what happens to this thing? Well, this is a horizontal asymptote question, or an end behavior question. In the top, we've got a 5n squared. On the bottom, we've got a 2n squared. Those are the most significant terms in the top and the bottom, so we'll just go ahead and consider those. And the n squareds cancel out. We just look at the coefficients, and we get 5 halves. So 5 halves would be the limit of the sum. All right, once again, so what? Well, think about when we were doing the Riemann sums, the right rectangular area method and the left rectangular area method and the midpoint rectangular area method. When we were doing those Riemann sums, we had an n in each of these problems. Do you guys remember what the n stands for? Well, if you don't, go back and look in your notes, because me telling you is not as informative as you figuring it out yourself. But if you already remember, we know that n equals the number of rectangles we divided the area up into. It's the number of sub-intervals that we divided our interval into. So why do we care about letting n go to infinity? Well, we already talked about this on the worksheet, I believe, or the intro worksheet, that n goes to infinity means that the number of rectangles is getting bigger and bigger and bigger. Each rectangle is getting infinitely small, infinitely skinny. The change in x is getting very, very small. but the number of rectangles is getting bigger and bigger and bigger. And what we found was that the error between the approximation and the actual got smaller and smaller and smaller. If n goes to infinity, we find not an approximation of the area, but the exact area. Exclamation mark. That's exciting.